The Sun has been burning for 4.6 billion years. Not metaphorically burning, not glowing in the way that a light bulb glows, through resistance and electrical current and the excitation of a filament. Burning in the most violent sense available in nature. Nuclear fusion reactions in the core are converting hydrogen into helium at a rate of approximately 600 million tons per second, every second, without pause, for 4.6 billion years. The same reactions that are happening right now as you read these words have been happening continuously since before the Earth existed, since before the Moon existed, since before any of the rocky planets existed. The Sun was already burning when the solar system was a disk of gas and dust, slowly organizing itself into planets and asteroids and comets. 600 million tons of hydrogen converted to helium every second. 600 million tons. The largest nuclear weapon ever detonated, the Soviet Tsar bomber of 1961, with a yield of approximately 50 megatons, converted approximately 2.8 kilograms of mass into energy. The Sun converts 600 million tons, that is 6 times 10 to the 11 kilograms, every second. The Tsar bomber represented the most energetic thing humanity had ever deliberately created. The Sun creates the equivalent of approximately 200 billion Tsar bombers worth of energy every second, continuously, for 4.6 billion years, and it will continue for another 5 billion years. The question that follows from this is immediate and obvious, and has been asked by every child who has been told the Sun is like a giant ball of fire. Why doesn't it go out? If the Sun is burning, really burning, consuming fuel at the rate described above, it should have burned out long ago. A candle burns for a few hours. A bonfire burns for a few days. Even the largest coal fire imaginable, all the coal ever mined in human history burned simultaneously, would be exhausted in some finite time that is inconceivably small compared to 4.6 billion years. What is the Sun burning that lasts so long? Why has 4.6 billion years of burning at 600 million tons per second not extinguished it? The answer to this question is one of the most important scientific discoveries ever made. A discovery that required developing not just new physics, but an entirely new way of thinking about energy and matter and what it means to burn something. The answer changed cosmology, changed our understanding of the age of the universe, changed biology's understanding of how long evolution had to work with, and changed physics in ways that took decades to fully absorb. Tonight, we are going to follow this question all the way down. Not to the quick answer, which exists and is correct, but leaves the physics behind in ways that cost more than they save, all the way down to what hydrogen fusion actually is, how it works, why it produces the energy it produces, what holds the Sun together, and what prevents it from exploding or collapsing, and what the eventual answer to the question of why it doesn't burn out is, which turns out to be not that it never burns out, but that it burns out slowly enough that the timescale involved is genuinely incomprehensible by any ordinary standard. Before we begin, if you are here because the quiet hours need something to fill them, stay. What follows is worth the time it takes. Let us start at the beginning. Let us start with the question of what burning actually is, because the word is used loosely in ways that obscure the physics, and understanding the physics is essential for understanding why nuclear burning is so different from chemical burning. Ordinary burning, the kind that happens in a candle or a bonfire or a coal fire, is a chemical reaction. Specifically, it is a rapid oxidation, the combination of a fuel with oxygen to produce oxides and release energy. When a carbon-containing fuel like wood or coal burns in air, carbon atoms in the fuel combine with oxygen molecules in the air to form carbon dioxide. Hydrogen atoms in the fuel combine with oxygen to form water. The chemical bonds in the products, carbon dioxide and water, are stronger and lower in energy than the bonds in the starting materials, fuel and oxygen. The excess energy is released as heat and light. The energy released in a chemical reaction comes from the rearrangement of electrons in atoms. Electrons in lower energy configurations have less potential energy. When they rearrange from a higher energy configuration, fuel plus oxygen, to a lower energy configuration, combustion products, the difference in potential energy is released. The amount of energy released per reaction is determined by the difference in electron configurations between the starting materials and the products. Chemical reactions release energy measured in electron volts per reaction, typically a few electron volts for a combustion reaction. 1 electron volt is approximately 1.6 times 10 to the negative 19 joules. This sounds small because it is small. It is the energy of a single chemical bond, which is a tiny amount of energy by any macroscopic standard. The reason burning releases appreciable energy on human scales is that the number of reactions occurring simultaneously in a burning material is enormous, on the order of 10 to the 23 reactions per mole of fuel. So the tiny energy per reaction multiplies to appreciable total energy. But the total energy available is still limited by the chemistry. You can only rearrange the electrons so much. The carbon-oxygen bond in carbon dioxide is the lowest energy configuration available to carbon and oxygen. You cannot get more energy out of that reaction by burning the products. Chemical energy is exhausted when all the fuel has been converted to the lowest energy combination with available oxidizer. Now consider what happens if, instead of rearranging electrons, you rearrange the nuclei themselves. Nuclear reactions. Instead of carbon combining with oxygen to form carbon dioxide, a rearrangement of electron configurations, you take 2 atomic nuclei and fuse them together to form a different nucleus. Or you take a heavy nucleus and split it into lighter nuclei. Fission. In either case, you are changing not the electron configurations, but the nuclear configurations, the arrangement of protons and neutrons in the nucleus. The energy involved in rearranging nuclear configurations is enormously larger than the energy involved in rearranging electron configurations. The forces holding nuclei together, the strong nuclear force, are approximately 100 times stronger than electromagnetic forces at nuclear scales. The energy scale of nuclear reactions is measured in millions of electron volts, mega electron volts, rather than the few electron volts of chemical reactions. A single fusion reaction releases millions of times more energy than a single chemical reaction. This is the fundamental reason nuclear burning lasts so much longer than chemical burning for the same mass of fuel. When you burn a kilogram of hydrogen chemically, combining it with oxygen to form water, you release approximately 120 megajoules of energy. When you fuse a kilogram of hydrogen nuclei into helium nuclei, nuclear burning, you release approximately 6.3 times 10 to the 14th joules, 630 terajoules. This is approximately 5.25 million times more energy from the same mass of fuel through nuclear fusion compared to chemical combustion. The Sun is running on nuclear fusion. If the Sun were running on chemical combustion, burning in the ordinary sense, it would have been exhausted in approximately 10,000 years. This was actually calculated in the 19th century by Hermann von Helmholtz and Lord Kelvin, who were trying to understand what powers the Sun. They determined that if the Sun were made entirely of coal burning in oxygen, it would have burned out long before geological evidence indicated Earth had been habitable. This was one of the famous 19th century conflicts between physics and geology. Geologists and biologists needed hundreds of millions of years for their processes, and the best available physical model of the Sun's energy source could only provide tens of thousands. Helmholtz and Kelvin proposed an alternative: gravitational contraction. If the Sun were slowly contracting under its own gravity, the gravitational potential energy released by the contraction could power the Sun's luminosity. They calculated that this mechanism could sustain the Sun for approximately 20 million years, much longer than chemical burning, but still far shorter than what geology and biology required. The conflict between physics and geology remained until the 20th century, when nuclear physics was developed and stellar nuclear fusion was identified as the true energy source. The identification of nuclear fusion as the solar energy source and the detailed theoretical description of the specific nuclear reactions responsible was achieved primarily in the late 1930s by Hans Bethe and Carl Friedrich von Weizsäcker, working independently. Bethe's 1939 paper on energy production in stars is one of the landmark papers in astrophysics, laying out the specific nuclear reaction chains that power the Sun and other stars with sufficient detail to calculate the expected luminosities and compare them to observations. Bethe received the Nobel Prize in Physics in 1967 for this work. Now let us go into the specific nuclear physics of what is actually happening in the Sun's core, because the answer to why the Sun doesn't burn out is rooted in the specific character of these reactions and the specific conditions under which they occur. The core of the Sun occupies approximately the innermost 25% of the solar radius, a sphere approximately 175,000 kilometers in radius. In this region, the temperature is approximately 15 million Kelvin, and the pressure is approximately 250 billion times atmospheric pressure at Earth's surface. The density is approximately 150 grams per cubic centimetre, about 150 times the density of water, and approximately 12 times the density of solid lead. At 15 million Kelvin, atoms cannot exist in their normal form. The thermal energy is sufficient to completely strip all electrons from all atoms. The material in the solar core is a fully ionized plasma of bare nuclei and free electrons. The hydrogen nuclei, which are simply protons since hydrogen nuclei contain only one proton and no neutrons, are moving at velocities of hundreds of kilometers per second, colliding with each other and with helium nuclei billions of times per second. Most of these collisions do nothing. The protons fly toward each other, are repelled by the electromagnetic repulsion between their positive charges, the Coulomb barrier, and fly apart again without fusion occurring. Fusion requires the two protons to get close enough that the strong nuclear force, which operates only at distances of approximately 10 to the negative 15 meters, can overcome the electromagnetic repulsion and bind them together. At the temperatures in the solar core, the thermal velocities of the protons are insufficient to overcome the Coulomb barrier through classical physics alone. This is where quantum mechanics becomes essential. Quantum mechanics introduces a phenomenon called quantum tunneling, the ability of a particle to pass through a potential energy barrier that it classically does not have enough energy to overcome. In quantum mechanics, a particle does not have a precisely defined position. It has a probability distribution that extends into regions that are classically forbidden. This probability decreases exponentially with the width and height of the barrier, but it is never exactly zero. A proton approaching the Coulomb barrier therefore has a small but non-zero probability of tunneling through the barrier and arriving on the other side in the region where the strong nuclear force dominates. Quantum tunneling of protons through the Coulomb barrier is the fundamental physical process that makes stellar nuclear fusion possible. Without quantum tunneling, the solar core temperature of 15 million Kelvin would be insufficient for fusion. The protons would never get close enough for the strong nuclear force to act. With quantum tunneling, a small fraction of proton-proton collisions result in fusion even at 15 million Kelvin. The probability of tunneling for any given collision is tiny, approximately 10 to the negative 28 or so. But the number of collisions per second in the solar core is so enormous that the total fusion rate is substantial. This tiny tunneling probability is in fact crucial for answering the question of why the Sun doesn't burn out quickly. The Sun's fusion rate is determined by the probability of quantum tunneling through the Coulomb barrier, and this probability is low enough that the Sun burns slowly. If the tunneling probability were higher, if fusion were easier, the Sun would burn faster and exhaust its fuel sooner. If it were lower, the Sun would burn dimmer and last longer, but produce insufficient energy to sustain life on orbiting planets. The specific value of the strong nuclear force coupling constant and the fine structure constant together determine the probability of quantum tunneling in stellar conditions, and the specific values these constants have in our universe result in fusion rates that give main sequence stars lifetimes of billions of years, long enough for stellar nucleosynthesis to enrich the interstellar medium, for planetary systems to form and evolve, and for life to emerge. The specific fusion reactions occurring in the solar core are primarily those of the proton-proton chain, a sequence of nuclear reactions that transforms 4 protons into one helium-4 nucleus through a series of intermediate steps. Let us go through these steps precisely, because the details matter for understanding both the energy produced and the byproducts that carry information about the reactions. The first step of the proton-proton chain is the fusion of 2 protons to form a deuterium nucleus, a nucleus containing 1 proton and 1 neutron. This reaction also produces a positron, the antimatter equivalent of an electron, and a neutrino. The reaction can be written as proton plus proton yields deuterium plus positron plus electron neutrino. This first step is the rate-limiting step of the entire chain. It is the slowest reaction, controlled by the weak nuclear force which mediates the conversion of a proton to a neutron. And it is this slowness that ultimately determines the Sun's lifetime. The mean lifetime of a proton in the solar core, before it undergoes this reaction, is approximately 10 billion years. A single proton, on average, waits 10 billion years before fusing. The Sun's 10 billion year main sequence lifetime is directly set by this reaction rate. The positron produced in this first reaction immediately meets a free electron, which are abundant in the solar plasma, and annihilates, producing 2 gamma-ray photons. The neutrino escapes the Sun essentially instantaneously. Neutrinos interact so weakly with matter that the entire Sun is transparent to them. They travel from the core to the surface and then to Earth in approximately 8 minutes and 20 seconds, passing through the Earth and through you right now without interaction. Approximately 65 billion solar neutrinos pass through every square centimetre of your skin facing the Sun every second. The second step of the proton-proton chain is rapid compared to the first. The deuterium nucleus produced in the first step quickly fuses with another proton to produce a helium-3 nucleus and a gamma-ray photon. The helium-3 nucleus contains 2 protons and 1 neutron. The third step has 3 possible branches. In the most common branch, accounting for approximately 85% of the proton-proton chain reactions in the Sun, 2 helium-3 nuclei fuse to produce 1 helium-4 nucleus and 2 protons. The 2 protons are released back into the plasma to participate in future reactions. The net result of this dominant branch, called pp-1, is that 4 protons have been converted into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and gamma-ray photons. The net mass change in this reaction is approximately 0.7%. 4 protons have a combined mass of 4.031 atomic mass units. The helium-4 nucleus has a mass of 4.003 atomic mass units. The difference, approximately 0.028 atomic mass units, has been converted entirely into energy according to Einstein's E equals mc squared. This 0.7% mass to energy conversion is the fundamental efficiency of hydrogen fusion. Every kilogram of hydrogen burned to helium releases approximately 6.3 times 10 to the 14th joules, as stated earlier. The rate at which the Sun consumes hydrogen is determined by dividing its total luminosity by the energy released per kilogram of hydrogen burned. The Sun's luminosity is approximately 3.8 times 10 to the 26 watts, 3.8 times 10 to the 26 joules per second. Dividing by 6.3 times 10 to the 14 joules per kilogram gives approximately 6 times 10 to the 11 kilograms per second, 600 million metric tons per second. This is the number we started with. It is derived from first principles of nuclear physics, not an empirical guess, but a calculated consequence of Einstein's mass-energy equivalence applied to the specific nuclear reactions occurring in the solar core. Now let us turn to the question of how much hydrogen the Sun has available, because the answer to why the Sun doesn't burn out is ultimately about the ratio of fuel available to the rate at which it is consumed. The Sun's total mass is approximately 2 times 10 to the 30 kilograms. Approximately 70% of this mass is hydrogen, approximately 1.4 times 10 to the 30 kilograms of hydrogen. However, not all of this hydrogen is available as fuel for core fusion. Fusion only occurs in the core, the innermost approximately 25% of the solar radius, where the temperature is sufficient for quantum tunneling at a rate that produces significant energy. Hydrogen in the outer layers is at temperatures far too low for fusion and is not consumed. Approximately 10% of the Sun's total mass, roughly 2 times 10 to the 29 kilograms, is hydrogen in the core, available for fusion during the main sequence lifetime. At a consumption rate of 6 times 10 to the 11th kilograms per second, This hydrogen will last approximately 2 times 10 to the 29th divided by 6 times 10 to the 11th seconds, approximately 3.3 times 10 to the 17 seconds. Converting to years, there are approximately 3.15 times 10 to the 7 seconds in a year, gives approximately 10.5 billion years. The Sun is approximately 4.6 billion years old. It has already consumed roughly 44% of its core hydrogen. Approximately 5.4 billion years of core hydrogen fusion remain. This is consistent with detailed stellar evolution models that predict a main sequence lifetime of approximately 10 billion years for a star of the Sun's mass and composition. 10 billion years. This is the answer to why the Sun doesn't burn out on any timescale that matters to human experience, or even to geological and biological timescales. The fuel reservoir, the core hydrogen available for fusion, combined with the slow rate at which quantum mechanical tunneling allows fusion to proceed, gives a total burning time of 10 billion years. Neither the amount of fuel nor the rate of burning alone is sufficient to answer the question. It is specifically the ratio, the enormous fuel reserve, divided by the quantum mechanically limited burning rate, that gives the enormous lifetime. This answer reveals something deeper than the specific numbers. It reveals that the Sun's longevity is a consequence of specific physical constants, the values of the strong nuclear force coupling, the weak nuclear force coupling, the electromagnetic coupling, and the mass of the proton, that together determine both how much fuel the Sun contains and how quickly it is consumed. Had these constants been different, had the strong nuclear force been slightly stronger, making fusion slightly easier, the Sun would burn faster and last less long. Had the weak force been different, changing the probability of the first proton-proton step, the rate would change. The specific combination of physical constants in our universe produces stars that last billions of years, long enough for planetary systems to develop and for life to evolve. This connection between the values of fundamental physical constants and the existence of observers capable of noticing those constants is one of the most discussed aspects of the fine-tuning problem in physics and cosmology. The observation that the constants appear calibrated in ways that permit complex structures, including life, to exist. Now let us talk about what keeps the Sun from exploding or collapsing, because a gas at 15 million Kelvin under enormous pressure should expand explosively, and the fuel consumption should be altering the star's structure continuously in ways that might destabilize it. Why doesn't the Sun simply detonate like one enormous thermonuclear bomb? The answer lies in a phenomenon called hydrostatic equilibrium, the balance between gravity and pressure that characterizes the internal structure of a stable star. Every layer of the Sun is in equilibrium between two opposing forces. Gravity pulls each layer inward toward the center, the weight of all the material above it pressing down. Pressure, both gas pressure from the thermal motion of particles and radiation pressure from photons diffusing outward, pushes each layer outward. When these two forces balance exactly at every layer, the star is in hydrostatic equilibrium and its structure is stable. The stability is self-regulating in a way that makes it remarkably robust against perturbation. If the core temperature increases slightly, perhaps due to a fluctuation, the fusion rate increases because quantum tunneling probability is temperature sensitive. More energy is produced. The core pressure increases. The core expands slightly. expansion cools the gas. This is thermodynamics. Expansion of a gas causes it to cool. The lower temperature reduces the fusion rate. The core contracts slightly, back toward equilibrium. The process is a negative feedback loop. Perturbations from equilibrium produce restoring forces that drive the system back toward equilibrium. This thermostat-like self-regulation is why the sun burns steadily rather than explosively. The nuclear reactions are temperature regulated through the expansion and contraction of the core. If you somehow tried to compress the solar core to make it denser and hotter, the fusion rate would increase, producing more pressure, expanding the core, and undoing your compression. If you tried to cool the core to reduce fusion, the reduced pressure would allow gravity to compress the core, raising the temperature, increasing fusion, and restoring the energy output. The self-regulation operates on timescales that are short compared to the sun's main sequence lifetime. The thermal timescale, on which the sun would respond to perturbations in its heat content, is approximately 15 million years. This means that any perturbation to the sun's equilibrium is corrected within 15 million years. A long time in human terms, but short compared to the 10 billion year main sequence. The sun has been in a stable, self-regulating state for its entire 4.6 billion year lifetime, and will remain so for another 5.4 billion years. The sun cannot detonate like a bomb because the pressure increase that a detonation would require would immediately cause expansion, which would cool the core, reduce the fusion rate, and prevent the runaway that a detonation requires. A thermonuclear bomb detonates because the bomb's material is not in hydrostatic equilibrium. It is assembled specifically so that the fusion reactions can run away before the material expands and quenches them. The sun's hydrostatic equilibrium prevents exactly this runaway. Let us now talk about what the energy produced in the solar core actually does on its journey from the core to the surface, because the journey of a photon from the center of the sun to the surface is one of the most counterintuitive processes in astrophysics. A photon produced in the solar core is a gamma-ray photon, high-energy electromagnetic radiation with wavelengths of approximately 10 to the negative 11 meters. This photon travels at the speed of light, but almost immediately encounters another particle, a free electron in the solar plasma. The photon scatters off the electron and travels in a new direction. It travels another tiny distance, typically measured in centimeters, before encountering another electron and scattering again, and again, and again. This process, photon scattering in the solar interior, is what makes the transport of energy from the core to the surface so slow. In the inner two-thirds of the sun, the primary energy transport mechanism is this radiative diffusion, photons undergoing countless scattering events as they slowly work their way outward. The average distance a photon travels between scatterings in the solar core is approximately 1 centimeter. The sun's core radius is approximately 175,000 kilometers, 1.75 times 10 to the 10 centimeters. A random walk, in which each step is 1 centimeter, requires approximately the square of the total distance divided by the step length in steps to traverse the total distance. Approximately 1.75 times 10 to the 10 squared equals approximately 3 times 10 to the 20 scattering events to cross the core. The total path length travelled by the photon, the sum of all these individual centimetre scale steps, is approximately 3 times 10 to the 20 centimetres, or approximately 3 times 10 to the 18 metres, or approximately 100 parsecs, about 300 light years. The photon travels the equivalent of 300 light-years before emerging from the solar core, even though it only needs to cover 175,000 kilometers of actual distance. This random walk through the solar interior takes approximately 100,000 to 200,000 years. During those 100,000 years, the photon is continuously absorbed, re-emitted, scattered, and rescattered. Each interaction changes the photon's wavelength as well as its direction. The high-energy gamma-ray photons produced in the core are gradually degraded into lower-energy photons. By the time the energy works its way to the solar surface, it has been distributed across the photon spectrum, and the typical photon emerging from the photosphere is a visible light or near-infrared photon with a wavelength of roughly 500 nanometers, consistent with the Sun's surface temperature of approximately 5,778 Kelvin. This means the sunlight reaching your eyes right now left the solar surface approximately 8 minutes ago. But the energy in that sunlight was produced in nuclear reactions in the solar core approximately 100,000 years ago. The photon that carries it to you has been in the Sun for 100,000 years, bouncing around in an enormously complicated random walk before it finally escaped from the photosphere and began its 8-minute journey to Earth. The outer third of the Sun, the convective zone, uses a different energy transport mechanism. In this region, the opacity of the solar material to radiation is high enough that radiative diffusion alone cannot carry the energy flux outward fast enough. Instead, convection takes over. Hot plasma rises from the bottom of the convective zone to the top, dumps its energy at the photosphere through radiation, cools, and sinks back down. This convective circulation is what produces the granular appearance of the Sun's surface. Each granule is a convective cell approximately 1,000 kilometers in diameter, lasting approximately 8 minutes before dissolving and being replaced by new granules. The surface of the Sun is covered in millions of these granules at any given time, boiling and churning as the convective heat transport delivers energy from the interior to the surface. The solar neutrinos produced in the core take a very different path. Because neutrinos interact so weakly with matter, their cross-section for interaction with any other particle is approximately 10 to the negative 45 square meters, the entire Sun is essentially transparent to them. A neutrino produced in the solar core travels through the Sun in approximately 2.3 seconds, at the speed of light, without interacting with anything. It then crosses the 150 million kilometers to Earth in approximately 8 minutes. It passes through Earth, through the entire planet, through the rock and the mantle and the inner core, and out the other side without interacting. The detection of solar neutrinos on Earth is therefore a direct measurement of what is happening in the solar core right now, not 100,000 years ago when the energy was produced, but now. Solar neutrino detectors, large tanks of various materials buried deep underground to shield them from cosmic rays, detect the rare interactions between solar neutrinos and the detector material at rates of a few events per day in the largest detectors. The measured neutrino flux matches the predictions of solar fusion models with impressive precision, providing direct confirmation that the proton-proton chain reactions described above are indeed what is powering the Sun. There was a historical puzzle called the solar neutrino problem. For decades, the measured solar neutrino flux was approximately 1/3 of the predicted value. This discrepancy was finally resolved in the early 2000s by the discovery of neutrino oscillations, the quantum mechanical phenomenon by which neutrinos transform between their three possible types, electron, muon, and tau neutrinos, as they travel. The early detectors were sensitive only to electron neutrinos, the type produced in the proton-proton chain. By the time the solar neutrinos reached Earth, approximately 1/3 were still electron neutrinos, and 2/3 had oscillated to the other types. The total neutrino flux, summing all three types, matches the solar model predictions. This resolution of the solar neutrino problem was one of the first clear demonstrations that neutrinos have mass, a discovery that earned Takaaki Kajita and Arthur MacDonald the 2015 Nobel Prize in Physics. Let us now talk about what will eventually happen to the Sun, because the answer to why the Sun doesn't burn out is incomplete without addressing the fact that it will eventually burn out, just on a timescale that dwarfs everything in human experience. In approximately 5.4 billion years, the hydrogen in the solar core will be exhausted. At that point, the nuclear reactions that have sustained hydrostatic equilibrium for 10 billion years will cease. The core, no longer supported by fusion pressure, will begin to contract under gravity. The contraction releases gravitational potential energy, the Kelvin-Helmholtz mechanism that Helmholtz and Kelvin had identified in the 19th century, which heats the core. Meanwhile, the hydrogen burning continues in a shell surrounding the now helium core. The increased energy output from the shell burning causes the outer layers of the Sun to expand dramatically. The Sun will become a red giant, swelling to perhaps 200 times its current radius, engulfing Mercury and Venus and possibly Earth. The outer layers will cool from 5,778 Kelvin to perhaps 3,500 Kelvin, shifting the colour from yellow-white to red. The luminosity will increase dramatically despite the lower surface temperature because the surface area increases so dramatically. Area scales as radius squared, so doubling the radius quadruples the luminosity for the same surface temperature. The red giant phase will last approximately 1 billion years. During this phase, the contracting helium core will heat to approximately 100 million Kelvin, hot enough to ignite helium fusion. The helium fusion reaction, the triple alpha process in which 3 helium-4 nuclei fuse to produce one carbon-12 nucleus, begins in a sudden energetic event called the helium flash. The helium flash releases approximately 10 to the 43 joules of energy in a period of a few minutes, more energy than the Sun radiates over hundreds of thousands of years of normal operation. But because this energy is deposited in the deep core and must diffuse outward through the same radiative and convective processes that govern normal solar energy transport, the helium flash has no immediately observable effect on the Sun's surface appearance. After the helium flash, the Sun settles into a new equilibrium, the horizontal branch, burning helium in the core and hydrogen in a shell. This phase lasts approximately 100 million years. When the helium in the core is exhausted, the pattern repeats. The core contracts, heats, helium burning continues in a shell, and the outer layers expand again. The Sun becomes an asymptotic giant branch star, even larger and more luminous than the red giant phase. The asymptotic giant branch phase is characterized by intense mass loss. The Sun will shed its outer layers in a series of thermal pulses and stellar winds, creating an expanding shell of gas, a planetary nebula, illuminated by the hot remnant core. What remains after the outer layers are expelled is the bare core, approximately 0.54 solar masses of mostly carbon and oxygen, compressed to approximately Earth's size. A white dwarf. This white dwarf will have a surface temperature of perhaps 100,000 Kelvin initially, and will cool slowly over billions to trillions of years, eventually becoming a cold, dark remnant at the ambient temperature of the universe. The white dwarf is supported not by nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. A white dwarf is the endpoint of stellar evolution for stars with initial masses less than approximately 8 solar masses, which includes the Sun. It is not burning, it is glowing from residual heat, slowly cooling, supported against gravity by the quantum pressure of its degenerate electrons. The Sun, therefore, does eventually burn out, but on a timescale of approximately 10 billion years from its formation, with an additional few billion years of evolved phases before the final white dwarf remnant. The question of why it doesn't burn out is answered not by claiming it never will, but by explaining why the specific ratio of fuel to burning rate gives such an enormous lifetime. A lifetime determined by the specific values of the physical constants that govern both the amount of hydrogen available and the quantum mechanical rate at which it can be consumed. Let us now talk about the broader context, about what stellar lifetimes tell us about the universe and about our own existence within it. The Sun's 10 billion year main sequence lifetime is not typical for all stars. It is specific to stars of the Sun's mass. More massive stars burn hotter and faster. Stars of 10 solar masses live approximately 30 million years. Stars of 0.1 solar masses burn so slowly that their main sequence lifetime is approximately 10 trillion years, 1,000 times longer than the current age of the universe. No star with less than approximately 0.8 solar masses has yet lived long enough to exhaust its hydrogen. The universe is not old enough. Every low-mass star that has ever formed is still on the main sequence. The diversity of stellar lifetimes has profound implications for the existence of life. Life, as we understand it, requires a complex mix of heavy elements: carbon, oxygen, nitrogen, phosphorus, iron, that are not products of Big Bang nucleosynthesis. They were produced in the interiors of earlier generations of stars and distributed into the interstellar medium through stellar winds and supernova explosions. A planetary system around the first generation of stars, stars formed from the primordial Big Bang composition of almost entirely hydrogen and helium, would have no rocky planets and no chemistry capable of supporting life as we know it. It required multiple generations of stellar birth and death to enrich the interstellar medium sufficiently with heavy elements to allow planetary systems like ours. Our solar system formed approximately 4.6 billion years ago from a molecular cloud already enriched by the deaths of previous generations of stars. This enrichment process, stellar nucleosynthesis, spread through the galaxy over billions of years, is why life on Earth depends so intimately on the lifetimes and deaths of stars that existed before the Sun formed. The Sun itself will contribute to this enrichment process at the end of its life. The planetary nebula it will shed, the expelled outer layers, will enrich the surrounding interstellar medium with helium, carbon, nitrogen, and other elements processed in the Sun's interior. The material expelled will eventually, over hundreds of millions of years, be incorporated into new molecular clouds and new stellar systems. The atoms in your body will eventually, most of them, return to the interstellar medium and contribute to the chemistry of new stars and new planetary systems billions of years from now. This cycle, stellar formation, nuclear burning, stellar death, enrichment of the interstellar medium, new stellar formation, is the mechanism by which the universe builds chemical complexity over time. Each generation of stars enriches the next. The specific lifetimes of each stellar generation, determined by the quantum mechanical physics of nuclear tunneling, determine the pace at which this enrichment proceeds. The 10 billion year lifetime of Sun-like stars gives enough time for planets to form and for life to evolve before the star exhausts its fuel and enters the dramatic phases of its death. But not so long that the enrichment process is delayed beyond usefulness. The question of why the Sun doesn't burn out connects, through the chain of reasoning we have followed, to some of the deepest questions in physics and cosmology. Why do the physical constants have the values they have? Why is the universe old enough for stars to have completed multiple generations of nucleosynthesis? Why does stellar nuclear fusion proceed slowly enough to give planetary systems billions of years of stable stellar energy? These questions do not have answers that all physicists agree on. They connect to the fine-tuning problem, to the anthropic principle, to the multiverse hypothesis, to questions about the fundamental nature of physical law. What is agreed on is the physics of the level we have been discussing. The proton-proton chain is well established. The solar neutrino flux has been measured. The solar model, the detailed theoretical description of the Sun's internal structure, agrees with observations to impressive precision. Helioseismology, the study of oscillations of the solar surface driven by acoustic waves in the solar interior, provides a direct probe of the Sun's internal structure and has confirmed the predictions of the standard solar model at the level of a few tenths of a percent in the sound speed profile throughout the Sun's interior. The picture is well understood, and the answer to the central question is clear. The Sun doesn't burn out because nuclear fusion is not ordinary burning. It releases millions of times more energy per unit mass. The specific mechanism, quantum tunneling of protons through the Coulomb barrier, is so improbable per collision that even with billions of collisions per second per proton, the consumption rate is slow. The Sun's enormous mass provides a fuel reserve measured in septillions of tons. The combination of enormous fuel reserve and quantum mechanically limited burning rate gives a total lifetime of 10 billion years, a number that is not incidentally large, but is specifically set by the physical constants that govern the rates of nuclear reactions and the mass of stars of the Sun's type. We are at the midpoint of the Sun's main sequence lifetime. It has burned for 4.6 billion years. It will burn for another 5.4 billion years in essentially the same way it burns today, slowly consuming its hydrogen, maintaining hydrostatic equilibrium through the self-regulating feedback between fusion rate and core temperature, delivering photons to Earth that were produced in nuclear reactions 100,000 years ago, and sending neutrinos that were produced moments ago directly through Earth and through you without pause. The star is not going out. Not today, not in any time frame that bears any relationship to human experience or even to geological or evolutionary timescales. It is burning exactly as it has burned since before the Earth existed, and exactly as it will burn long after everything that has ever lived on Earth has been gone. Let us talk about what the Sun's steady burning means for the history of life on Earth. Because the 4.6 billion year stable energy output of the Sun is not merely a backdrop to the history of life, but one of its primary enabling conditions. And understanding the relationship between stellar physics and biological evolution illuminates both subjects. Life on Earth has existed for approximately 3.8 to 4 billion years, nearly as long as the Earth has existed. The oldest confirmed microfossils date to approximately 3.5 billion years ago, and chemical signatures of biological activity in ancient rocks push the record to approximately 3.8 to 4 billion years. This means life appeared on Earth very quickly after the planet cooled sufficiently to have liquid water, within a few 100 million years of Earth's formation. The rapidity of life's appearance suggests that the origin of life is not extraordinarily improbable given the right conditions, or at least that it happened once and has persisted continuously since. For the first approximately 2 billion years of Earth's history, all life was single-celled and microscopic. Bacteria and archaea dominated the biosphere. The Cambrian explosion, the sudden diversification of complex multicellular life in the fossil record, occurred approximately 540 million years ago. Complex animals, plants, and fungi have existed for only approximately 500 to 600 million years, about 1/8 of the Sun's age, and about 1/8 of Earth's history. The stability of the Sun's energy output over these timescales is crucial. Life did not just need solar energy at the beginning, it needed it continuously and relatively steadily for billions of years. A star that flickered, dimmed, or brightened significantly on geological timescales would have disrupted the climatic and chemical conditions that allowed the slow evolution of complex life. The self-regulating feedback mechanism that keeps the Sun's output steady, the thermostat we described earlier, has maintained a remarkably constant luminosity over billions of years. Not perfectly constant. The Sun has brightened slightly over its lifetime as helium accumulates in the core and the mean molecular weight of the core material increases, causing the core to contract and heat slightly, increasing the fusion rate and luminosity. The Sun today is approximately 30% more luminous than it was 4.6 billion years ago. This gradual brightening has influenced Earth's climate in ways that geologists and climate scientists are still working to fully understand. The faint young sun paradox is one of the most interesting puzzles in the history of climate science. Given the Sun's lower luminosity 3 to 4 billion years ago, simple climate models predict that the Earth should have been frozen. Global temperatures should have been below the freezing point of water for much of early Earth history. Yet the geological record shows liquid water, seas, rivers, and shallow marine environments at exactly these early times. Life was thriving in liquid water environments 3.5 billion years ago, when the Sun was 20 to 25% dimmer than today. The resolution of the faint young sun paradox likely involves higher concentrations of greenhouse gases, primarily carbon dioxide and methane, in Earth's early atmosphere. Higher CO2 concentrations would have provided additional greenhouse warming sufficient to compensate for the reduced solar luminosity. As the Sun has brightened over billions of years, the geological carbon cycle has gradually reduced atmospheric CO2 concentrations through increased weathering rates at higher temperatures, keeping Earth in the habitable zone despite the brightening star. This geological thermostat, the carbon cycle's regulation of atmospheric CO2 in response to temperature, has operated in concert with the slowly brightening Sun to maintain a relatively habitable Earth for billions of years. This connection between stellar physics and planetary habitability is one of the most remarkable aspects of our situation. The 10 billion year main sequence lifetime of a Sun-like star is long enough for planetary systems to form, for geological processes to establish themselves, for life to originate, and for evolution to produce intelligent observers. The specific lifetime is set by the quantum mechanical tunneling probability we discussed, the probability of proton-proton fusion through the Coulomb barrier. This probability is set by the values of the strong nuclear force and the electromagnetic force. Had these constants been different, the fusion more efficient or less efficient, the main sequence lifetime would be shorter or longer, and the specific combination of timescales needed for intelligent life might or might not have been available. This is not a proof of design or fine-tuning in any metaphysical sense. It is an observation about the specific combination of physical constants that characterizes our universe, and the specific combination of timescales that this combination permits. Whether this combination is the only possible one, or one of many in some larger ensemble of universes, or the result of some deeper physical principle that determines the constants, these are open questions in physics and cosmology that the current state of knowledge cannot resolve. What can be said is that the Sun's longevity, the specific answer to why it doesn't burn out for billions of years, is not a coincidence unconnected to our existence as observers asking the question. It is part of the physical context within which we exist. The same physics that allows us to ask the question provides the conditions, stable stellar energy over billions of years, without which the asking would be impossible. Let us now talk about what helioseismology has taught us about the Sun's interior. Because the ability to probe the inside of a star using acoustic waves that ripple across its surface is one of the most elegant scientific techniques of the modern era, and it has provided confirmation of the solar fusion model at a level of precision that would have seemed impossible 50 years ago. The Sun's surface oscillates, not violently. The oscillations are measured in meters per second of velocity, invisible to the naked eye, detectable only by precision Doppler spectroscopy. The Sun rings like a bell struck by the turbulent convection in its outer layers, and the ringing is complex. The surface oscillates in thousands of different modes simultaneously, each with a specific frequency and spatial pattern. These acoustic modes are called P modes, pressure modes, in which the restoring force is gas pressure, and they have periods of approximately 5 minutes for the most common observed modes. The key insight is that different acoustic modes sample different depths in the solar interior. Just as seismologists can determine Earth's internal structure by analyzing how seismic waves travel through the interior and emerge at different points on the surface, helioseismologists can determine the Sun's internal structure by analyzing how acoustic waves propagate through the solar interior. The frequency and pattern of a given acoustic mode depends on the sound speed profile throughout the solar interior, the way in which the sound speed varies with depth. The sound speed, in turn, depends on the temperature, density, and composition at each depth. By measuring the frequencies of thousands of acoustic modes with high precision, using networks of ground-based telescopes positioned around the world to provide continuous coverage, and space-based instruments like the Solar Dynamics Observatory and the SOHO satellite, helioseismologists have been able to invert the problem and deduce the sound speed profile throughout the solar interior, from the surface up to the core. The sound speed profile derived from helioseismology agrees with the predictions of the standard solar model, the theoretical model of the Sun's internal structure derived from the physics of stellar structure and the proton-proton chain, to better than 0.5% throughout most of the solar interior. This agreement is one of the most precise confirmations of a theoretical model in all of astrophysics. The solar fusion model correctly predicts the internal structure of the Sun as directly probed by acoustic waves. The small remaining discrepancy approximately 1% in the region just below the convective zone, is one of the more interesting current problems in solar physics. It is likely related to uncertainty in the solar composition, specifically the abundances of the heavy elements that contribute to the solar opacity. Revisions in the measured solar heavy element abundances in the 2000s improved the spectroscopic analysis of the solar composition, but created a discrepancy between the helioseismologically inferred structure and the standard solar model built with the new abundances. This solar abundance problem is an active area of research, and its resolution will require either revision of the solar model physics or better observational constraints on the solar composition. Helioseismology has also allowed the measurement of the Sun's internal rotation, how fast different layers of the Sun rotate. The Sun rotates differentially. The equator rotates faster than the poles. At the surface, the equatorial rotation period is approximately 25 days, and the polar rotation period is approximately 35 days. Helioseismology shows that this differential rotation extends through the convective zone, but transitions to approximately solid body rotation in the radiative interior. The entire radiative zone rotates at roughly the same rate as the surface at mid-latitudes. The transition layer between differential rotation in the convective zone and solid body rotation in the radiative zone, called the tachocline, is thought to be the site where the Sun's magnetic field is generated through a dynamo process. The 11-year sunspot cycle, the periodic variation in solar activity, sunspot number, and solar magnetic field, is driven by this magnetic dynamo operating in the tachocline. The magnetic field is amplified and organized by the differential rotation and the convective flows, emerging through the solar surface as sunspot groups, active regions, and coronal structures. The solar cycle affects the solar irradiance at Earth by approximately 0.1%, a small variation that nevertheless has measurable effects on Earth's upper atmosphere and may contribute to climate variability on decadal timescales. The magnetic activity of the Sun also drives the solar wind, the continuous outflow of charged particles from the solar corona. The corona, as discussed in other contexts, is the outermost layer of the solar atmosphere, and its temperature of 1 to 3 million Kelvin drives a constant outflow of plasma at speeds of 400 to 800 kilometers per second. This solar wind bathes the solar system with energetic particles, shapes the magnetospheres of the planets, and defines the heliosphere, the bubble of solar-influenced space that we discussed in the context of Voyager's crossing into interstellar space. The solar wind represents a form of mass loss from the Sun, approximately 10 to the negative 14 solar masses per year. Over the Sun's 4.6 billion year lifetime, this amounts to approximately 0.04% of the Sun's mass, a tiny but non-zero contribution to the total mass shed. This is small compared to the mass converted to energy in fusion. Approximately 0.03% of the total mass has been converted to energy over the Sun's lifetime. But the solar wind affects the Sun's angular momentum and the orbital dynamics of the planets in ways that are important over geological timescales. Let us talk about what the internal composition of the Sun tells us about its history, because the current composition of the solar interior is a direct record of the nuclear burning that has occurred over 4.6 billion years. At the formation of the solar system, the Sun's initial composition was approximately 71% hydrogen, 27% helium, and approximately 2% heavier elements by mass, a composition typical of stars that formed in the Milky Way approximately 4.6 billion years ago, after multiple generations of stellar nucleosynthesis had enriched the interstellar medium. This initial composition is still observed in the solar surface and the outer layers of the convective zone, where nuclear reactions do not occur and the original composition is preserved. In the core, the composition has changed substantially. The 4.6 billion years of proton-proton chain reactions have converted approximately 4% of the total solar mass, which represents approximately 40% of the core's initial hydrogen, from hydrogen to helium. The core is now approximately 35% hydrogen and 63% helium by mass, compared to the initial approximately 71% hydrogen and 27% helium. The helium produced by fusion has accumulated in the core, gradually increasing the mean molecular weight and requiring the core to slowly contract and heat to maintain hydrostatic equilibrium. This gradual increase in the core's helium abundance and the corresponding slow contraction and heating is what drives the slowly increasing luminosity of the Sun over its lifetime. As the mean molecular weight increases, the core must be hotter and denser to produce the same pressure, increasing the fusion rate and luminosity. The solar luminosity has increased approximately 30% over 4.6 billion years for this reason. The rate of increase will continue through the remaining main sequence lifetime, and by the time the core hydrogen is exhausted in approximately 5.4 billion years, the Sun will be approximately 60% more luminous than today. The composition profile within the Sun, how the hydrogen and helium abundances vary with depth, has been probed by helioseismology, which is sensitive to composition through its effect on the sound speed. The boundary between the convective zone, where convective mixing maintains relatively uniform composition, and the radiative zone, where the composition varies with depth according to the nuclear burning history, can be identified in the helioseismic data. The base of the convective zone sits at approximately 0.713 solar radii, a boundary that is consistent with the predictions of the standard solar model. Now let us talk about what other types of stars tell us about the robustness or fragility of the specific nuclear burning mechanism that powers the Sun. Because the proton-proton chain is not the only way stars can burn hydrogen, and understanding the alternatives illuminates the specific character of solar burning. More massive stars, those with initial masses greater than approximately 1.3 solar masses, have core temperatures high enough that a different nuclear reaction chain dominates hydrogen burning. This is the CNO cycle, a catalytic cycle in which carbon, nitrogen and oxygen nuclei act as catalysts for converting hydrogen to helium. The net reaction is the same as the proton-proton chain, 4 protons converted to 1 helium-4 nucleus with the same energy release per reaction, but the mechanism is different and the rate has a much stronger temperature dependence. In the CNO cycle, a carbon-12 nucleus absorbs a proton to produce nitrogen-13, which is unstable and decays to carbon-13. Carbon-13 absorbs another proton to produce nitrogen-14. Nitrogen-14 absorbs a proton to produce oxygen-15, which decays to nitrogen-15. Nitrogen-15 absorbs a proton and produces carbon-12 plus helium-4. The original carbon-12 is regenerated and can participate in the next cycle. The net effect is that 4 protons have been consumed and 1 helium-4 has been produced. The same result as the proton-proton chain, but via a completely different mechanism. The CNO cycle rate scales approximately as temperature to the 17th power, an extremely steep temperature dependence compared to the proton-proton chain, which scales approximately as temperature to the 4th power. This steep temperature dependence means that the CNO cycle is extremely sensitive to core temperature and operates efficiently only above approximately 17 million Kelvin. In the Sun's core, at 15 million Kelvin, the CNO cycle contributes only approximately 1% of the total energy production. The proton-proton chain dominates overwhelmingly. In more massive stars with hotter cores, the CNO cycle dominates and the proton-proton chain is negligible. The strong temperature dependence of the CNO cycle has important consequences for stellar structure. More massive stars that burn primarily via the CNO cycle have much more concentrated energy production in their cores. The steep temperature dependence means that a slightly hotter central region produces enormously more energy, creating large temperature gradients that drive convection in the stellar core. The cores of massive stars are convective, while their outer envelopes are largely radiative, the opposite of the Sun structure, where the core is radiative and the outer third is convective. This structural difference affects how massive stars evolve and how they distribute their nuclear processed material. Convective cores in massive stars mix the nuclear products throughout the core, bringing fresh hydrogen from the outer core into contact with the hottest burning regions. Radiative cores in lower mass stars like the Sun do not mix efficiently. The hydrogen and helium are stratified by depth according to their molecular weight. This difference in mixing affects the main sequence lifetime, the composition of the products expelled in stellar winds and supernova explosions, and the structure of the remnant after the star dies. Understanding both the proton-proton chain and the CNO cycle, and the conditions under which each dominates, is part of understanding why different stars have different lifetimes, different interior structures, and different contributions to the chemical enrichment of the galaxy. The Sun runs on the proton-proton chain. Massive stars run on the CNO cycle, the same fundamental nuclear physics, protons combining under the influence of the strong nuclear force, with quantum tunneling through the Coulomb barrier enabling the reactions at stellar temperatures, underlies both, but the specific mechanism and its temperature dependence create very different stellar behaviors. There is a small contribution from the CNO cycle in the Sun, approximately 1%, and detecting the specific neutrinos produced by CNO cycle reactions in the solar core is one of the goals of current neutrino physics experiments. The Borexino experiment in Italy, a spherical detector containing 280 tons of liquid scintillator buried under 1.4 kilometers of rock in the Gran Sasso mountain, has detected neutrinos from several specific branches of the proton-proton chain and made the first detection of CNO cycle neutrinos from the Sun in 2020. This measurement confirmed that the CNO cycle is operating in the solar core at the level predicted by the standard solar model, and provided new constraints on the solar heavy element abundance, relevant to the solar abundance problem mentioned earlier. Let us now talk about what other stellar phenomena illuminate the process of nuclear burning and the question of stellar longevity. Specifically, the remarkable objects called pulsars and neutron stars, which are not burning in the nuclear sense, but whose properties illuminate extreme physics relevant to stellar energy production. When a massive star, more than approximately 8 solar masses, exhausts all of its nuclear fuel in the core, it undergoes core collapse. The iron core, which cannot release energy through fusion because iron is the most stable nucleus, the peak of the nuclear binding energy curve, collapses catastrophically in less than a second. The collapse halts when the core reaches nuclear density, approximately 4 times 10 to the 17 kilograms per cubic meter, and the nuclear matter becomes incompressible. The infalling outer layers bounce off the rigid proto-neutron star and the combined energy of the collapse, approximately 3 × 10⁴ joules, is released primarily as neutrinos in a few seconds. This is a supernova. The neutrino burst from a supernova, detected for the first time in 1987 when supernova 1987A in the Large Magellanic Cloud occurred, is the most energetic event observable in astronomy per unit time. The approximately 10⁵ neutrinos released in a few seconds carry approximately 99% of the total energy of the collapse. The remaining 1%, approximately 10⁴ joules, drives the visible explosion. Even so, the visible explosion briefly outshines the entire host galaxy, containing perhaps 200 billion other stars. The remnant left behind, if the collapsing core is not so massive that it forms a black hole, is a neutron star. A neutron star contains approximately 1 to 2 solar masses in a sphere approximately 20 kilometers in diameter. Its density is comparable to atomic nuclei, neutrons and protons packed together at nuclear density. A neutron star is supported against gravity not by nuclear burning, it is not burning at all, but by neutron degeneracy pressure, the quantum mechanical pressure arising from the Pauli exclusion principle applied to neutrons. Neutron stars are not burning in the nuclear sense. The neutron degeneracy pressure that supports them does not consume any fuel. It is a property of quantum mechanics, not of nuclear reactions. A white dwarf, supported by electron degeneracy pressure, and a neutron star, supported by neutron degeneracy pressure, are the endpoints of stellar evolution for stars below and above the threshold for neutron star formation, respectively. Above approximately 2 to 3 solar masses of neutron star mass, even neutron degeneracy pressure cannot support the star against gravity, and it collapses to a black hole. The existence of objects supported by quantum degeneracy pressure, white dwarfs and neutron stars, rather than by nuclear burning, raises an interesting contrast with the Sun. The Sun is sustained by the ongoing energy production of nuclear fusion. If you somehow stopped the fusion, if you could turn off the proton-proton chain, the Sun would not immediately collapse. It would slowly contract over approximately 15 million years, the thermal timescale, as it radiated away its thermal energy without replacing it. The eventual fate would be a degenerate object, in the Sun's case ultimately a white dwarf, after the red giant and planetary nebula phases described earlier. White dwarfs and neutron stars represent the final state, objects that have run out of fuel but that are supported against gravity by quantum mechanical effects that do not require fuel consumption. They are the answer to what a star looks like after it has burned out. The Sun will become a white dwarf. Massive stars leave neutron stars or black holes. Neither type requires ongoing burning to exist. They are stable quantum mechanical configurations that will persist for timescales vastly longer than any nuclear burning phase. The white dwarf that the Sun will eventually become will cool slowly from its initial surface temperature of perhaps 100,000 Kelvin toward the ambient temperature of the universe. The cooling timescale is long. Simple estimates suggest that a white dwarf takes approximately 10 billion years to cool to temperatures at which it becomes invisible, a black dwarf. The universe is not yet old enough for any white dwarf to have cooled completely. The oldest known white dwarfs have cooled for approximately 12 billion years and are still at measurable temperatures. In the far future, after tens of billions of years, the white dwarf remnants of all the stars formed during the stellar era will gradually become black dwarfs, cold, dark objects at the ambient temperature of an increasingly cold and dark universe. Let us now talk about what the Sun's nuclear burning means in the context of Einstein's famous equation, because E equals mc squared is not merely a formula that physicists write on chalkboards. It is the physical principle that explains every aspect of the question we are examining, and its implications extend far beyond stellar physics into the deepest foundations of how we understand matter and energy. Einstein derived E equals mc squared in 1905 as part of his development of special relativity. The equation says that mass and energy are equivalent, that mass is a form of energy and energy is a form of mass. The proportionality constant is c squared, the speed of light squared, which is an enormous number, approximately 9 times 10 to the 16th joules per kilogram. This means that a small amount of mass corresponds to an enormous amount of energy. Before Einstein's insight, the law of conservation of energy and the law of conservation of mass were considered separate laws of nature. Chemical reactions conserved both. The mass of products equaled the mass of reactants, and the energy of products equaled the energy of reactants. This was confirmed to extraordinary precision by careful chemical experiments. What Einstein showed is that these two conservation laws are actually one law, the conservation of mass energy. In chemical reactions, the conversion between mass and energy is so small as to be unmeasurable by any 19th century technique. The mass of the products of a chemical reaction is slightly less than the mass of the reactants. The mass difference corresponds to the energy released, but the amount is approximately 10 to the negative 10 of the total mass. If you burn a kilogram of wood, the products weigh approximately 10 nanograms less than the starting materials, unmeasurably small. In nuclear reactions, the mass to energy conversion is millions of times larger. In the proton-proton chain, 0.7% of the mass of the fusing hydrogen is converted to energy. This is still a small fraction, less than 1%, but it is measurable, and it has been confirmed in precise measurements of nuclear masses. The mass of a helium-4 nucleus is measurably less than the mass of 4 hydrogen nuclei. The difference is exactly what E equals mc squared predicts should have been converted to energy. The nuclear mass measurements that confirm E equals mc squared have been made with extraordinary precision using mass spectrometers, instruments that measure the mass of individual nuclei by determining how their trajectories are bent in magnetic fields. Atomic masses are known to 10 or more significant figures for most nuclei. The mass deficit in nuclear reactions, the difference between the mass of the reactants and the mass of the products, agrees with the measured energy release to the same precision. Einstein's equation is confirmed as precisely as any equation in physics. This confirmation has profound practical consequences. Nuclear power plants and nuclear weapons work because E equals mc squared is correct. The energy released in nuclear fission and fusion is the mass difference between reactants and products converted by the factor c squared. Particle accelerators work because the kinetic energy of colliding particles can create new particles with mass, energy converted to mass according to the same equation. The mass of a proton at rest is a consequence of the energy stored in the strong nuclear force fields binding its constituent quarks, mass as confined energy. The Sun's nuclear burning is therefore not just a stellar phenomenon. It is a demonstration of the most fundamental equivalence in physics, the equivalence of mass and energy, operating at the scale of a stellar interior. Every photon that reaches Earth from the Sun carries energy that was mass, specifically hydrogen nucleus mass, 100,000 years ago, deep in the solar core. The light warming your skin is the converted mass of hydrogen nuclei. The warmth you feel is the echo of mass-energy conversion at 15 million Kelvin, under pressures of 250 billion atmospheres. This is not poetry. This is the precise physical chain of causation from the fundamental equations of physics to the photons arriving at your retina. E equals mc squared, applied to the proton-proton chain, gives the energy per reaction. Summing over all reactions in the solar core gives the solar luminosity. The solar luminosity, transported by the random walk of photons over 100,000 years through the solar interior, emerges at the photosphere at the right wavelength and intensity to warm a planet at the right distance to sustain liquid water and biological chemistry. The physical chain is complete and quantitative at every step. Understanding this chain, from Einstein's equations, through nuclear physics, through stellar structure, through photon transport, through the 8-minute journey to Earth, is understanding why the Sun burns without burning out. And understanding that is understanding something fundamental about the nature of the universe and our position within it. The Sun is not like a fire in any ordinary sense. It is a self-gravitating sphere of plasma whose structure is determined by the balance between gravity and pressure, maintained in stable equilibrium by a self-regulating feedback loop that keeps the nuclear burning rate constant over billions of years. The fuel is hydrogen. The burning is quantum mechanical tunneling of protons through the electromagnetic repulsion between their positive charges. The energy is the mass difference between the fuel and the products, converted according to Einstein's equation. The rate is set by the specific values of the physical constants governing the strong nuclear force, the electromagnetic force, and the quantum mechanical tunneling probability. The lifetime is the ratio of the available fuel to the consumption rate, approximately 10 billion years. The Sun will not burn out tomorrow. It will not burn out in 1,000,000 years or in 1,000,000,000 years. It is burning right now exactly as it has burned for 4.6 billion years, and as it will burn for another 5.4 billion years, slowly, steadily, self-regulated, sustained by an ocean of hydrogen that is consumed at a quantum mechanically limited rate that gives it a lifetime measured in billions of years. That lifetime is not eternal. The Sun will exhaust its core hydrogen, expand to a red giant, shed its outer layers, and leave a cooling white dwarf. But the timescale, the specific, calculated, physically grounded timescale of 10 billion years, is large enough to allow complex planetary systems, complex chemistry, complex biology, and complex minds to arise and ask the question of why it doesn't burn out. The answer is embedded in the question. The specific physics that sets the Sun's lifetime, quantum tunneling through the Coulomb barrier, the mass-energy equivalence of E equals mc squared, the hydrostatic equilibrium of self-gravitating gas, also sets the timescale available for the emergence of the complexity that asks the question. The Sun burns for billions of years because the physics that makes it burn also makes it burn slowly. And it burns slowly because the specific values of the physical constants in our universe produce quantum tunneling probabilities that make proton-proton fusion rate-limited in exactly the way needed for stellar lifetimes measured in billions of years. This is the answer to why the Sun doesn't burn out. Not just a number, 10 billion years, but the physics behind the number, and behind the physics, the constants that set it, and behind the constants, the universe that contains them, and the minds that arose within it to ask the question. Let us talk about what the Sun's nuclear burning looks like from the perspective of the individual proton, because tracing the experience of a single particle through the solar interior from the moment it is created to the moment it leaves the Sun as part of a photon is one of the most vivid ways of making the abstract physics of stellar fusion concrete and personal. A proton in the solar core exists in an environment of extraordinary density and temperature. The density of the solar core is approximately 150 grams per cubic centimetre, 150 times the density of water. In this environment, the proton is not alone. It is surrounded by approximately 10 to the 31 other protons and helium nuclei and free electrons per cubic metre. The mean distance between protons is approximately 10 to the negative 10 meters, roughly atomic distances, meaning the protons are essentially in contact with each other, in the sense that the distance between them is comparable to the size of an atom. At 15 million Kelvin, the proton is moving at a velocity of approximately 500 kilometers per second, about 0.17% of the speed of light. It travels this distance in straight lines between collisions. The mean free path between collisions is approximately 10 to the negative 11 meters, smaller than the size of a hydrogen atom. The proton undergoes approximately 5 times 10 to the 13 collisions per second, 50 trillion collisions every second. Each collision deflects the proton in a new direction. The proton's trajectory is a chaotic, random walk through the dense plasma. In the vast majority of these collisions, the proton simply bounces off another proton through electromagnetic repulsion. The protons approach, are repelled by the Coulomb barrier, and scatter in new directions. No fusion, no reaction, just elastic scattering that randomizes the proton's direction while maintaining the overall thermal distribution. Very occasionally, with a probability of approximately 10 to the negative 28 per collision, the quantum tunneling phenomenon allows the proton to penetrate the Coulomb barrier and approach close enough to another proton for the strong nuclear force to take over. Even then, fusion does not immediately occur. The two protons must form a diproton, a bound state of two protons, which is extraordinarily unstable because there are no neutrons to provide additional nuclear binding. The diproton must immediately emit a positron and a neutrino, converting one proton to a neutron through the weak nuclear force, to become a deuterium nucleus. This weak force process is the true rate-limiting step, and its probability per collision is even smaller than the tunneling probability. The mean waiting time for a proton in the solar core before it undergoes this first fusion reaction is approximately 10 billion years. Let that sit for a moment. A proton in the solar core undergoes 50 trillion collisions per second, approximately 1.6 times 10 to the 21 collisions per year, and it waits on average 10 billion years for one of those collisions to result in fusion. The probability of fusion per collision is approximately 10 to the negative 31, so low that even with the extraordinary collision rate, the average waiting time is billions of years. This is why the Sun lasts so long. Not because there is an enormous amount of fuel, though there is, but because the rate of fuel consumption is so extraordinarily slow per proton. Each proton in the core is essentially immortal on any human timescale. It bounces chaotically through the plasma, waiting for 1 billion years on average, before the specific quantum mechanical accident of tunneling and weak force decay combines to allow fusion. The Sun contains approximately 10 to the 57 protons in its core. At a mean fusion time of 10 billion years per proton, the number fusing per second is approximately 10 to the 57 divided by 10 to the 10 years times 3 times 10 to the 7 seconds per year. Approximately 3 times 10 to the 39 fusions per second. Each fusion reaction in the proton-proton chain ultimately converts 4 protons to 1 helium-4 nucleus and releases approximately 26 mega-electron volts of energy. Multiplying the fusion rate by the energy per complete pp chain cycle gives approximately the solar luminosity, 3.8 times 10 to the 26 watts. The calculation from first principles gives the right answer to within the uncertainties of the input parameters. The physics is consistent. After the proton finally fuses, after its billion-year wait, it becomes a deuterium nucleus. The deuterium nucleus does not wait long. Within approximately 1 to 4 seconds, it encounters another proton and fuses to form helium-3. The helium-3 nucleus then waits approximately 400 years before encountering another helium-3 and fusing to form helium-4. The entire proton-proton chain, from the initial proton-proton fusion to the final helium-4, takes approximately 400 years once the first slow step is complete. The billion-year wait for the first step dwarfs everything else. Now let us think about what happens to the energy released in that initial fusion event. The positron produced in the first step immediately annihilates with a nearby electron. This happens within approximately 10 to the negative 11 seconds. The annihilation produces 2 gamma-ray photons, each with an energy of approximately 0.511 mega-electron volts, the rest mass energy of an electron. These photons begin their journey toward the solar surface. The neutrino produced in the first step, an electron neutrino with an energy of at most 0.42 mega-electron volts, travels at the speed of light and exits the Sun in approximately 2.3 seconds. It has essentially 0 probability of interacting with anything in the Sun or on Earth. It passes through everything. Some tiny fraction of the neutrinos produced in the solar core, perhaps 1 in every 100 billion, will interact with a nucleus somewhere in the Earth and be detected by neutrino observatories. The gamma-ray photons begin their extraordinarily long journey. They travel approximately 1 centimeter, 10 to the negative 2 meters, before encountering another particle and scattering. In the dense plasma of the solar core, the primary scattering mechanism is Compton scattering, a photon striking a free electron and transferring some of its energy to the electron, emerging at a lower energy and a different direction. The energy transferred to the electron goes into the thermal energy of the plasma, heating it, while the photon continues on at lower energy. Each scattering event is a random walk step. The photon travels 1 centimeter in a random direction, scatters, travels another centimeter in a new random direction, scatters again. After n scattering events, the expected displacement from the starting point is the square root of n centimeters. To cross the core radius of 175,000 kilometers, 1.75 times 10 to the 10 centimeters requires approximately 1.75 times 10 to the 10 squared equals approximately 3 × 10⁻20 scattering events. At a density and scattering cross-section appropriate for the solar core, this takes approximately 170,000 years. During those 170,000 years, the photon is absorbed, re-emitted, Compton scattered, thermalized, re-emitted, and gradually loses energy as the higher energy photons are absorbed by the plasma and re-emitted as multiple lower energy photons. The original gamma-ray photon at 0.511 megaelectron-volts is progressively degraded in energy through countless interactions. By the time the energy has worked its way to the photosphere, the typical photon is in the visible range, approximately 2 electron-volts, having lost a factor of approximately 250,000 in energy per photon. But because the energy is conserved, the total energy arrives at the surface, there are correspondingly more photons carrying the same total energy. The one original high-energy gamma-ray photon has been replaced by approximately 250,000 visible light photons carrying the same total energy. These visible light photons emerge from the photosphere, the solar surface, and begin their 8-minute journey across the solar system to Earth. Some fraction of them reach Earth and interact with the atmosphere, with the oceans, with the land, and with living things. In leaves, they drive photosynthesis, the molecular machinery that captures solar photon energy and stores it in chemical bonds that can be used to power biological processes. In your skin, they warm you and drive the production of vitamin D. In your eyes, they are absorbed by photoreceptors and transduced into neural signals that become your visual experience of the world. The photon that enters your eye and is absorbed by a rhodopsin molecule in your retina carries energy that was mass, hydrogen nucleus mass, approximately 170,000 years ago in the solar core. The journey from hydrogen nucleus mass to your visual experience took 170,000 years of diffusion through the solar interior, 8 minutes of light travel, and a few nanoseconds of photochemical transduction in your retina. The total time from nuclear burning to perception is approximately 170,000 years. The nuclear event that produced the energy was quantum mechanical. The perception that registers the energy is biological. The physics connecting them is thermodynamics and electromagnetism and optics. This chain, from quantum mechanical tunneling in the solar core to visual perception in a biological eye, is one of the most remarkable causal chains in nature. It connects the smallest scales of physics, nuclear dimensions, to the largest, stellar, through a cascade of physical processes operating at every intermediate scale. The sun is not burning in a way that is separate from the universe that contains it. It is burning in a way that is woven into the fabric of the universe, setting conditions for planetary formation, for chemical enrichment, for biological evolution, and for the emergence of minds capable of following the causal chain from nuclear tunneling to conscious perception. Let us now talk about the specific number that answers the question of how long the sun has been burning and how long it will continue, not as an abstract fact, but as something that can be placed in the context of what that time means. 4.6 billion years. The sun has been burning for 4.6 billion years. To internalize what 4.6 billion years means requires comparison to things we can actually understand. If the sun's entire 10 billion year main sequence lifetime were compressed into one calendar year, 1 year beginning on January 1st, the sun formed on January 1st. The solar system formed during the first week of January. The Earth formed around January 6th or 7th. Life first appeared on Earth approximately in late February. Photosynthesis, the biological process that uses solar energy to fix carbon, appeared sometime in May. Complex multicellular life did not appear until approximately November 15th. The Cambrian explosion, the diversification of animal body plans, occurred approximately November 18th. The dinosaurs appeared approximately December 12th and were extinct by December 26th. Homo sapiens, our species, appeared approximately December 31st at approximately 11:46 p.m. All of recorded human history, from the first cities to the present moment, occurred in the last 15 seconds of December 31st. And the Sun's current position in its main sequence lifetime is approximately May 4th on this compressed calendar. It is just past the midpoint of its hydrogen-burning phase. The red giant phase begins approximately September 1st. The planetary nebula and white dwarf formation occur approximately in September and October. The white dwarf cools through the remaining months toward a black dwarf that will never quite form within the age of the universe. These comparisons do not make 4.6 billion years comprehensible in any direct way. The human nervous system simply does not have a module for comprehending billion-year timescales. What they do is give the number context. They show the ratios between different epochs and events, and the ratios are genuinely informative even if the absolute scale is not directly graspable. The ratio that matters most for our question is that recorded human history, 5,000 to 10,000 years, occupies approximately 15 seconds in the 10 billion year compressed calendar. All of human civilization, all of recorded history, every war, every invention, every work of art and science and philosophy, 15 seconds out of a year. The sun has been burning for the entire year. It will burn for another half year before the hydrogen runs out. We are here for 15 seconds of the year, or rather, we have been here for 15 seconds of the year so far, and we have developed enough understanding of physics and chemistry and nuclear processes to determine exactly why the sun is burning and how long it will continue. That is either an extraordinarily efficient use of 15 seconds or a remarkable coincidence that such questions can be answered in such a short time. It is probably both. Let us now talk about what other stars near us are doing, about the specific nuclear burning occurring in the stars visible in the night sky. Because the sun is not an isolated phenomenon, but one of billions of stars, all undergoing nuclear burning simultaneously throughout the galaxy. The nearest star to us is Proxima Centauri, a red dwarf located approximately 4.24 light-years away. Proxima Centauri is approximately 0.12 times the Sun's mass, a small star, barely above the minimum mass needed to sustain nuclear fusion. Its core temperature is lower than the Sun's, its fusion rate is much lower, and its main sequence lifetime is correspondingly much longer, approximately 4 trillion years. Proxima Centauri has barely begun its main sequence phase. It is burning at a tiny fraction of the Sun's luminosity, approximately 0.17%, and will continue burning long after the Sun has become a white dwarf, long after the Milky Way has merged with Andromeda, long after all the massive and intermediate mass stars in the galaxy have died. The very different lifetimes of different mass stars have a specific implication for life around them. A planet around Proxima Centauri, such as Proxima b, would have 4 trillion years of stellar energy available if it is in a habitable orbit and has an appropriate atmosphere. This is a vastly longer time window for the development of life and intelligence than Earth has had around the Sun. The question of whether the intense flaring activity of red dwarfs is compatible with life on their close orbiting habitable zone planets is a separate issue. But the sheer time available for evolution around red dwarfs is staggering compared to what was available around the Sun. Alpha Centauri A, the Sun-like star in the Alpha Centauri system, is approximately 1.1 times the Sun's mass and approximately 6 billion years old, older than the Sun by approximately 1.4 billion years. It is therefore further along its main sequence evolution than the Sun. Its core has burned a larger fraction of its hydrogen, its luminosity is somewhat higher than the Sun's current luminosity, and it has correspondingly fewer billions of years remaining before it exhausts its core hydrogen and begins to evolve off the main sequence. If Alpha Centauri A has a planet in its habitable zone, a possibility that remains scientifically uncertain, as discussed elsewhere, that planet has been receiving stable stellar energy for 6 billion years. Life on Earth appeared within the first billion years of Earth's existence. 6 billion years of solar-type irradiation is more than enough time for life to have appeared and evolved to significant complexity. Sirius, the brightest star in the night sky at approximately 8.6 light-years distance, is approximately 2 times the Sun's mass and, correspondingly, much more luminous, approximately 25 times the Sun's luminosity. Its main sequence lifetime is approximately 1 billion years. Sirius A is currently approximately 200 to 300 million years old, a young star by stellar standards. It has more than enough time remaining on the main sequence to allow planetary systems to form, but its 1 billion year total lifetime is short compared to the time that has been required on Earth for complex life to evolve. Whether this is sufficient time for life to evolve around a star like Sirius, assuming it has suitable planets, is an open question that bears on the broader question of how common life is in the universe. Betelgeuse, the red supergiant star in Orion, visible to the naked eye as the orange-red star at Orion's shoulder, is approximately 700 light-years away, and approximately 16 to 19 times the Sun's mass. It is at a very different stage of evolution from the Sun. It has already exhausted its core hydrogen and is burning helium in its core and hydrogen in a shell, having expanded to approximately 700 solar radii. It would extend beyond the orbit of Jupiter if placed at the Sun's position. Betelgeuse is approaching the end of its life. It would explode as a supernova within approximately the next 100,000 years, possibly much sooner, becoming briefly the brightest object in the sky after the Moon, visible during the day. The specific timing of Betelgeuse's supernova cannot be predicted precisely, because the late stages of massive stellar evolution are not well enough understood theoretically to allow exact timing. The diversity of stellar burning, from the trillion-year slow burn of red dwarfs to the million-year intense burning of massive blue stars to the imminent supernova of Betelgeuse, is a consequence of the single underlying physics of nuclear fusion, modulated by stellar mass. The same quantum mechanical tunneling, the same Coulomb barrier, the same proton-proton chain and CNO cycle, operating at different temperatures in different mass stars, produces this extraordinary range of stellar behaviors. The galaxy is filled with stars at every stage of this evolutionary progression. Young stars just beginning to burn, middle-aged stars like the Sun burning steadily, ancient red giants approaching the ends of their main sequence lives, and recent supernova remnants where massive stars have already completed the entire cycle and returned their processed material to the interstellar medium. This galactic ecosystem of stellar burning, the continuous cycle of star formation, nuclear burning, mass loss, and stellar death that has been operating for the 13.8 billion year history of the galaxy, is the mechanism by which the universe builds complexity over time. Each generation of stars processes primordial hydrogen and helium into heavier elements. Each stellar death distributes those elements into the interstellar medium. Each new generation of stars forms with slightly more heavy element enrichment than the previous generation. Over many stellar generations, the interstellar medium has been enriched to the current solar composition of approximately 2% heavy elements, the specific composition that allowed the formation of rocky planets, of water, of carbon-based chemistry, and of life. We are products of this enrichment process. The carbon in our cells was forged in helium-burning stars. The oxygen we breathe was produced in stellar cores and distributed by stellar winds and supernova explosions. The iron in our blood was synthesized in stellar explosions, some of it possibly in Betelgeuse's predecessors. The calcium in our bones and the phosphorus in our DNA came from the same stellar nucleosynthesis processes that have been operating throughout the history of the galaxy. The Sun is not just a provider of energy for the current moment. It is the most recent expression of a process that has been operating for 13.8 billion years. The process by which stars burn hydrogen to helium, process heavier elements in successive burning phases, and distribute the products of nuclear burning throughout the galaxy when they die. We are the downstream consequence of this process, the product of many generations of stellar burning that preceded the Sun's formation, and that left behind the heavy elements needed for planetary chemistry and biology. Understanding why the Sun doesn't burn out is therefore understanding not just the physics of one star, but the physical mechanism that underlies the existence of everything complex in the universe. Stars burning hydrogen to helium, slowly, steadily, over billions of years, regulated by quantum mechanics and hydrostatic equilibrium, is the process that has made everything else possible. The specific timescale, billions of years, is not incidental. It is determined by the physical constants that govern nuclear processes, and it is exactly long enough for the consequences of stellar burning, planetary formation, chemical enrichment, biological evolution, to develop. The Sun burns without burning out for billions of years because the universe is built in a way that makes billion-year stellar lifetimes possible. Because protons do not fuse easily, because the Coulomb barrier is high relative to the thermal energies available at stellar temperatures, because quantum tunneling makes fusion possible, but at low enough probability that consumption is slow, because E equals mc squared makes the energy release per fusion event enormous. Enormous enough that the slow consumption rate still produces the luminosity needed to warm orbiting planets. Because hydrostatic equilibrium stabilizes the burning against runaway and against premature quenching. Because the mass of a star like the Sun provides a fuel reservoir sufficient for 10 billion years at the quantum mechanically limited consumption rate. All of these pieces fit together, not by design but by physics, into a picture of stellar burning that is both deeply understood and deeply remarkable. The understanding came slowly. The first clue that the Sun was not a chemical fire came from geology in the 19th century. The identification of the energy source as nuclear fusion came in the late 1930s. The detailed understanding of the proton-proton chain and its specific rate came with the quantum mechanical calculation of tunneling probabilities. The confirmation of the solar model through helioseismology and solar neutrinos came in the latter half of the 20th century. Now we understand it. Not every detail, the solar abundance problem, the coronal heating problem, the details of the solar magnetic dynamo all remain active areas of research. But the central question, why does the sun burn without burning out, has a clear, precise, quantitative answer rooted in quantum mechanics and nuclear physics and thermodynamics. The answer is beautiful in the way that deep physical understanding is beautiful. Not just an explanation, but a unification of many apparently separate phenomena into a single, coherent picture. The sun is burning right now, exactly as it has burned for 4.6 billion years, at the rate set by quantum tunneling through the Coulomb barrier, in the equilibrium set by hydrostatic balance between gravity and pressure, converting hydrogen to helium at 0.7% mass to energy efficiency, according to E equals mc squared, producing 3.8 times 10 to the 26 watts of power, transporting that power through 100,000 years of radiative diffusion and convective churning, releasing it from the photosphere as visible light, sending it across 150 million kilometers in 8 minutes, and depositing it in your skin, in the leaves of plants, in the oceans and the atmosphere, as the warmth that sustains the biosphere that produced everything that has ever lived on this planet. It will continue for another 5.4 billion years. Not because it is eternal, but because the physics that makes it burn also makes it burn slowly. Because the quantum mechanical accident of Coulomb barrier tunneling is rare enough that each proton waits billions of years before fusing. Because the mass available is large enough and the consumption rate slow enough that the ratio, the lifetime, is measured in billions of years. That is why the sun doesn't burn out. Not forever, not in any time scale meaningful to human experience, not in any time scale meaningful to geological or evolutionary or even astronomical history on any scale that matters to us. The sun is burning. It has always been burning. It will continue burning long after everything that has ever mattered to human civilization has passed into history. The question of why this is so connects the smallest physics, quantum mechanics at nuclear scales, to the largest, the structure and evolution of stars and galaxies and the universe. The connection runs through Einstein's equation, through the proton-proton chain, through hydrostatic equilibrium, through the specific values of the physical constants that govern all of these phenomena. It is one of the most complete answers in physics. And the completeness is itself remarkable, that a question as simple as "why doesn't the sun burn out?" leads, when followed with sufficient rigour and curiosity, to some of the deepest and most beautiful physics in all of science. There is a specific kind of understanding that changes how you experience something ordinary. Not information about the thing, not facts that you could recite when asked. Understanding. The kind that changes what you see when you look at it. The kind that makes the familiar strange and the strange familiar simultaneously. The kind that arrives not as a sudden flash, but as a slow deepening that takes everything you thought you knew and shows you how much more is there. Looking at the sun is not something you can do directly. That is itself a physical fact worth noting, The star is too bright for direct observation, producing enough photons per square centimetre per second to permanently damage the photoreceptors in your retina within seconds of direct viewing. The star that sustains all life on this planet cannot be looked at. It can only be looked at indirectly, through the light it casts on everything else, through the warmth it deposits in everything it touches, through instruments that convert its energy into representations safe for biological visual systems to process. But you can feel it. Step outside on any day with open sky and turn your face toward the sun with your eyes closed. The warmth you feel on your skin is not incidental to what the sun is. It is the sun. The energy of nuclear reactions that occurred in the solar core 100,000 years ago, transported by countless photon scattering events through the solar interior, released from the photosphere 8 minutes ago, crossing 150 million kilometers of space to arrive at your face. The warmth on your skin is mass that was hydrogen nucleus mass 170,000 years ago, before human civilization existed, before modern Homo sapiens had spread across all the continents, before the last ice age. That mass was in the solar core, in the form of a proton that had been waiting in the churning plasma for the quantum mechanical accident of Coulomb barrier tunneling that would allow it to fuse. When the accident finally happened, when the proton finally fused after its billion-year wait, the mass-energy difference between the hydrogen fuel and the helium product began its long journey as a photon, working its way outward through the solar interior. Now it is here, in your skin, depositing the energy of E equals mc squared applied to a nuclear reaction that happened before human history began. This is not a metaphor. This is the literal, physical chain of causation that connects the quantum mechanical tunneling of a proton through a Coulomb barrier in the solar core to the warmth of sunlight on your face. Every photon in sunlight carries energy that was mass. Every warm day is a demonstration of Einstein's equation applied at stellar scale. Every green plant is a machine for capturing this mass-turned energy and storing it in chemical bonds. Every animal that eats plants is running on converted stellar mass. You are built from it too. The carbon in your cells was not present in the original hydrogen that formed the sun. It was synthesized in the nuclear burning phases of earlier generations of stars, stars that formed billions of years before the sun, burned through their hydrogen and helium and sometimes carbon and oxygen, and died in explosions that distributed the products of their nuclear burning into the interstellar medium. The molecular cloud from which the sun and its planets formed was already enriched with these products, already containing the carbon and oxygen and nitrogen and iron that would become the rocky planets, the oceans, the atmosphere, and eventually the chemistry of life. You are made of the nuclear ash of dead stars. Your carbon was forged in stellar interiors at temperatures of hundreds of millions of Kelvin. Your oxygen came from the same furnaces. Your iron was synthesized in supernova explosions of stars that died billions of years before the sun was born. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, all of it came from stellar nuclear burning that preceded you by billions of years. And the energy that animates this chemistry, that makes your heart beat and your neurons fire and your lungs expand, comes from the star burning overhead right now, which is still burning, as it has burned for 4.6 billion years at the rate set by quantum mechanical tunneling in the equilibrium set by hydrostatic balance, converting 600 million tons of hydrogen to helium every second. The sun is not going out. Not tomorrow, not in 1,000,000 years, not in 1,000,000,000 years. It has 5.4 billion years of hydrogen burning remaining in its core, a timescale so large that recorded human history fits into it approximately 540,000 times. All of recorded human history, from the first cities to this moment, 540,000 times before the sun's hydrogen runs out. The question, why doesn't the sun burn out, has a precise quantitative answer. It is the ratio of the available fuel, the core hydrogen, to the quantum mechanically limited consumption rate set by the probability of Coulomb barrier tunneling at 15 million Kelvin. The numerator is large because the sun is massive. The denominator is small because the strong nuclear force and the electromagnetic force and the weak nuclear force have specific values that make proton-proton fusion extraordinarily slow per collision. The ratio of these two quantities, measured in seconds divided by the number of seconds in a year, gives a number of approximately 10 billion. 10 billion years. The answer is not mystical. It is not approximate. It follows from the specific values of fundamental physical constants through specific calculations in nuclear physics and stellar structure theory. And it has been confirmed by helioseismology and solar neutrino detection to a precision of a few percent. The sun will burn for 10 billion years because of what it is made of and because of the specific rules that govern how what it is made of can react. But there is more than the answer. There is the chain of reasoning that leads to the answer, the chain that passes through quantum tunneling and the Coulomb barrier and the proton-proton chain and E equals mc squared and hydrostatic equilibrium and radiative diffusion and the random walk of photons and the thermal timescale and the main sequence and stellar evolution. Each link in this chain is a piece of physics that took real human effort to discover, decades of work by real scientists operating with real instruments and real equations, building on the work of those who came before, adding piece by piece to a picture that none of them individually could see in its entirety. That accumulated understanding is one of the most extraordinary achievements of the species that developed it. We are biological creatures that evolved to survive on the surface of a planet, to find food, to avoid predators, to navigate social groups. We were not built by evolution to understand nuclear quantum mechanics or stellar structure or mass-energy equivalence. These things are not adaptive in any direct sense. Understanding the proton-proton chain did not help any individual human survive or reproduce. And yet, we figured it out. We built the instruments and the mathematics and the theoretical frameworks to understand why a star 150 million kilometers away has been burning for 4.6 billion years and will continue for another 5.4 billion. This is the thing that the question, why doesn't the sun burn out, ultimately leads to. Not just the nuclear physics, not just the stellar evolution. The fact that there exist on a small planet orbiting the star in question, creatures made of the ash of earlier stars, animated by the energy of the current star, capable of asking and answering the question of why the current star burns without burning out. The matter organized itself through billions of years of stellar nucleosynthesis and planetary formation and chemical evolution and biological evolution into something that can understand its own origin and the physics of its own energy source. The sun is burning. You are here because it is burning. You understand why it is burning. All three of these things are true simultaneously, and the connection between them, the physical and biological chain that links stellar fusion to conscious understanding, is itself one of the most remarkable facts about the universe that we inhabit. Step outside. Feel the warmth on your face. Know what it is. Not just sunlight, not just energy. The converted mass of hydrogen nuclei fused in quantum mechanical accidents 170,000 years ago, delivered across 150 million kilometers of space in photons that have been traveling for 8 minutes, absorbed by the molecules of your skin into the thermal motion of their atoms. The sun is burning. It will be burning tomorrow. It will be burning when everyone alive today is gone. It will be burning when every building currently standing has crumbled. It will be burning in 1 billion years, when the continents have shifted into configurations that no current map shows, and when whatever life exists on Earth is as different from us as we are from the bacteria that first appeared in the ancient oceans. It burns because the physical constants of our universe make hydrogen nuclei hard to fuse, because quantum tunneling is rare, because E equals mc squared makes the energy release per fusion event enormous, because hydrostatic equilibrium prevents runaway, because the fuel reservoir is vast, because the rate is slow. It burns for the same reason anything in the universe happens, because the rules of physics, applied to specific initial conditions, produce specific outcomes on specific timescales. The timescale for the Sun is 10 billion years. We are here in the middle of it. We exist in the warmth of a star burning through its middle age, built from the ash of stars that burned before it, capable of understanding the physics of the burning. That is the full answer. Not just a number, the entire chain from quantum mechanics to warmth on your face to the understanding that explains both. The sun is not going out. Not yet.